Thanks for the invitation. Your introduction kind of reminds me that actually this is still just a continuation of my graduate school work. See, but I'm happy to be here. So this is the work I'm going to be talking about, Skermion pairing and DMRG evidence for a topological route to superconductivity. This was really spearheaded by my postdoc at Berkeley, Shibayu Chatterjee, whose background really is as a field theorist trained by Subir Sachdev, but he said he wanted to learn some DMRG when he got to Berkeley. So he basically picked the most difficult possible problem, testing for Skermions in a 4-component fermion model in 2 dimensions. And Matteo Ippoliti, who's probably, who I work with at Princeton, he's now a postdoc with Vedika Committee at Stanford, and he's probably the world expert in these sorts of numerics. This work is really kind of inspired by an earlier theory paper with our collaborators at Harvard. And there we were thinking about magic angle twisted bilayer graphene, and we came up with this idea for the Skermion mechanism. So a lot of the theory I'm going to be talking about is also developed in that paper there. Okay, so the outline for the talk, I'll start without any motivation in experiments, just defining a fairly simple model for you. And the claim is that this simple model has all electronic mediated superconductivity. And then because this is CCQ, I'm going to spend a little bit of time talking about the technical details of how we're able to solve for the ground state using DMRG. Then I'll present the DMRG evidence that pairing of topological textures, Skermions, leads to superconductivity. And then at the very end, I'll map this model we studied onto the physics of magic angle twisted bi or trilayer graphene. So hopefully we get to that point. Okay, so what's the model? We're going to be looking at interacting electrons moving in 2 dimensions. And the starting point is actually 2 stacked 2-dimensional electron gases. And both of them are spinful. So when I say stacked, I kind of think of it as maybe 2 layers of gallium arsenide, and I'll call the layers plus layer and the minus layer labeled by this index gamma. And then each of them is spinful. So altogether, you have 4 fermion orbitals that we can organize here into a super spinner here, and just have, say, quadratic dispersion. Okay, now I'm going to call them layer and spin, but they don't really need to be layer and spin. It could be like orbital and valley or something else. And when we do eventually apply this to bilayer graphene, it won't be layer and spin. There'll be some other degrees of freedom in that problem. Okay, but this is just the notation I'm going to use. Okay, the next ingredient is we add usual long-range Coulomb repulsion, 1 over r repulsion between them. And note that the interaction is the total density and the total density. So all 4 components talk equally strongly with each other. It's not, even though I said layer, we don't actually bring the 2 layers apart. It's a SU4 symmetric interaction at this point. And then there's one final ingredient, which is that I want an anti-ferromagnetic interaction between the spins in the top layer and the spins in the bottom layer. So that's this 3rd term I've added here. One way to depack it is it's convenient to define these n vectors, 1 for each layer, which is just a vector associated to the spin polarization in that layer. So it's the layer resolved spin. And then this 3rd term I'm adding into the Hamiltonian is just the difference in the magnetization squared. Or if you expand it out, it's just the usual Heisenberg coupling between the spin in the top layer and the spin in the bottom layer, which prefers them to always anti in a line. Okay, so that lets us draw pictures, kind of like a nonlinear sigma model. For the spin configurations, I have a unit sphere, both the top layer and the bottom layer, and you always want them to point opposite on that sphere. Now, the first 2 terms are, of course, any 2-day would have them. The 3rd might seem a little bit unnatural. But actually, you can think of this J as an effect that would arise whenever you take the first 2 terms and then add a little bit of hopping between the 2 layers. Because if you do this in a perturbative regime, you could perturbatively account for hopping from 1 layer and then back, and then that would generate super exchange, just like in the Fermi-Hubbard model. That would actually generate the sort of anti-ferromagnetic coupling I'm talking about. So it's quite natural to have this term. Okay, so this model alone, I don't believe would be a superconductor, at least not for small j, because you just have 1 over r Coulomb repulsion. There's very strong repulsion between the particles. But the claim is that if we just make 1 small change to this Hamiltonian, which is the top layer I'm going to put a magnetic field coming out of the plane, and the bottom layer I'm going to put a magnetic field equal and opposite into the plane. So the claim is if you put this magnetic field on, you get lambda levels in each layer, but of course they're strongly talking to each other through the Coulomb interaction. But anyway, if you go to a filling factor of 2 plus a little bit, so you like dope it away from 2, that this model is a superconductor for any positive value of J, even though you have 1 over our Coulomb equation. So that's the claim. I find it pretty surprising, and I want to use DMRG to actually, solve the ground state and show that that's true, and give some intuition for why. It's going to be an exotic mechanism, as I've alluded to, Skermion. Okay, so what's the numerical approach? Since this is CCQ, I'll indulge a little bit in how we do this. Ignoring the interactions for the moment, let's just look at the single particle term. We just have 2 conventional Landau level spectrum, one for the plus layer and one for the minus layer. And when you solve for the cyclotron gaps, they don't depend on the sign of the magnetic field. So you get identical spectrum for both of them. So on the plus side, in every Landau level, you get a spin up and a spin down. They're degenerate, and so on. And then there's just a mirror image in the minus side. Okay, so that means that the 0th Landau level actually has 4 Landau levels in it, from up, down, and then the layer index. So when we're filling the lowest Landau level, that's the filling running from 0 to 4, and so on and so forth. Okay, then as we often do in these quantum Hall-like problems, if the magnetic field becomes large, then the gap, the cyclotron gap, becomes much larger than the Coulomb interaction, and it becomes well-defined to project the interaction into the lowest flat bands, i.e. the lowest Landau level. So that's what we're going to do. We're going to take that Hamiltonian and project it into the lowest Landau level. And then the problem's actually quite standard to similar fractional quantum numerics, which is why I'm not actually doing anything too different with my life at this point. But it's rather complicated because we have 4 components coming from spin and layer. Now, where does the sign of B show up? Well, if you write down the wave functions in the Landau levels, they're going to be related by complex conjugation. You have this holomorphic form that in the lowest Landau level, everything's a holomorphic function, so it'll be anti-holomorphic in the minus layer. And when you go to calculate the Coulomb matrix elements, this phase factor shows up, and that little change of that phase factor is actually going to lead to superconductivity. Okay, so just looking at one component, how do we study it using DMRG? This general approach actually goes way back, before my work. I think the earliest was probably Shibata back in 2001. And the idea is DMRG, of course, is a 1D method. So we need to take our 2D Hamiltonian and map it to a 1D chain. The way we do it is we first put the problem on a cylinder, so that one axis is long and one axis has circumference L. And then we use this nice Landau gauge on the cylinder, in which at the single particle wave level, the wave functions take this cool form, where it's a plane wave indexed by momentum k around the cylinder, this term here. And then it's Gaussian localized along the length of the cylinder, where the center of mass, the average position, is locked to whatever the momentum around the cylinder is. Okay, so it's this form here. And because we're on a cylinder, the momenta are quantized in units 2 pi over L. So you get a set of discrete orbitals this way, which you don't need to discover a weird snake order or something. They're just obviously, in a line from left to right. Okay, so that's our mapping to a 1D fermion Hamiltonian. Now, when we add these other components, we basically just need to take 4 copies. So 2 of them are identical coming from spin, and you just splice them together, their orbitals. And then the other 2 copies, the wave functions are kind of reversed. For a given momentum, the way the sign of the magnetic field shows up is whether the center of mass increases with momentum or decreases. So what we're going to have is 2 sets of our Landau level are spiraling to the right with momentum, and the other moving to the left, but you can still just interleave them according to where their center of mass positions. Okay, so we have this unit cell with 4 components in it. Anyone want to stop me there? Okay, at that point, we have our single particle basis, and we have this Hamiltonian. You just need to do all the matrix elements by evaluating integrals with respect to the Coulomb interaction and so on, and then you turn it into some very complicated 4 fermion interaction Of course, it has translation invariance and some degree of locality, but it's not like looking at the nearest neighbor Hubbard model. And the reason is when you look at these Gaussian orbitals, their width is a magnetic length, let's just call that 1, and the distance between them scales inversely with the circumference. So by the time you're at the circumferences we look at, 10 or 12, every orbital's overlapping with 10 or 12 other orbitals, or actually more like 40 once you include spin. So any term in this four-body Hamiltonian, if you pick an orbital, it's going to be interacting with, I don't know, 10,000 other terms in this Hamiltonian. So it's a quite complicated Hamiltonian. But nevertheless, we can go to circumferences of 8 or 12. So it's not really a thin cylinder, it's a medium cylinder. And the way we do this, I need to give credit. This was my graduate's work with Roger Mong and Frank Pullman. We have our DMARG code 10pi, which is able to kind of automatically handle all this using MPO compression, density matrix corrections, and so on. Okay, so that made this whole project a lot easier having it too.
So Mike, can I ask a question?
Yeah.
This is just a simple physics question. So because your interaction you made the point of saying that it's kind of like beyond or not at all like a Hubbard model because there's many different orbitals which are overlapping with each other. Do you think that then it becomes more realistic than the Hubbard model, or this is kind of just a numerical thing?
Like more realistic as far as like magic angle twisted bilayer graphene, or?
Well, okay, I was more thinking more realistic in that Coulomb is long range and not like Hubbard.
Oh, well, I mean, I guess, you probably need someone else to pipe it. I mean, my understanding is Hubbard is a 3D material. It's not too poor an assumption to think that you have screening of Coulomb interaction. But these 2D, you have a 3D Coulomb interaction, but only really a 2D material. So it's generally, if you have dielectric response, it can't really screen itself. Now I have glossed over one detail, which is in most of these sort of Van der Waals experiments, there's a metal gate some distance away, and then the metal is finally able to screen the 1 over R off to an exponential. And our numerics actually include that. It's just that the length of the gate is quite larger than LB, like 5 or something. And I can kind of assure you that the physics really doesn't depend on having this gate there, is what I'm going to say would hold true even for 1 over R.
Can I ask a question too?
Yeah.
So, so you're like, just to make sure I understood correctly, you're doing infinite DMRG and you just need the 4 strike unit cell. That's to have the 4, like the plus and minus and the top and bottom layer degrees of freedom.
Yeah.
And then you just encode these long range interactions with MPO compression. Is that essentially the? Just, could you? I mean, I don't know very well about this, but I thought there's like pseudo potential methods where I can evaluate these long range Coulomb matrix elements. Couldn't I just do that and just have a Hamiltonian that has many terms in it?
Yeah, I mean, the first step is that, just like you do in quantum chemistry or anything, you just evaluate the matrix elements and you get these numbers V, A, B, C, D. The issue is that there's just a lot of them. Like if you pick any one site, there might be 10,000 non-zero V, A, B, C talking with it. And if you naively try and just make the MPO, you could do it, but you'd find that the size of this matrix product operator would be like bond dimension 10,000 or something.
Okay.
So we need some way without affecting the precision to just like make it smaller. And it turns out there's just like tricks you can use. Like if you have an interaction which is an exponential, that can actually be written as a low rank matrix product operator, and that allows you to do a sort of compression. So yeah, when we do this, we don't change, like the Hamiltonian is represented to like 10 to the -5 accuracy, so it's not really an issue.
And you don't actually present these interactions, like these 10,000 terms, you don't put them, you just have the whole expression and you compress the MPO somehow. Is that?
Yeah. I mean, we first need to actually evaluate the 10,000 matrix elements. That will take like a half hour or something, and then after the fact, you compress them.
Okay. All right. Thanks.
Okay, so what's the phase diagram? Well, in the model I discussed so far, the only real knob was the density and then this strength of this J term. But it's going to be convenient partly to compare with magic angle graphene, to generalize the anti-ferromagnetic interaction a little bit, in that rather than making it completely SU2 symmetric, I can couple the X, Y, and Z part slightly differently, and I'm going to use this XXZ anisotropy. So in the XY plane, it's going to be the same strength, and then the Z plane can be different by this factor called lambda. So J is the average, and lambda is the XXZ anisotropy. So when we do this, there's no longer SU2, but there still is a spin rotation symmetry about the Z axis, which is going to play an important role. That symmetry, if we do map to magic angle graphene, corresponds to the Valley rotation, the Valley U1 conservation. Okay, and we're going to measure units in terms of the magnetic length, which is the natural length scale. It's kind of like the lattice cutoff, and the Coulomb energy, E squared over LB. And then we're going to measure the strength of the anti-ferromagnetic term in units of EC, so that J and lambda are just some dimensionless numbers. So let me give you a schematic of what the phase diagram looks like. We fix a particular filling, and generally we're going to be interested in going to like 2 and then doping it a little bit, so 2 plus delta. And then we look at the phase diagram as a function of J and lambda, and generally what's going to happen is that for larger J, we're going to find it's a superconductor. Then there's a first order phase transition along some line at the critical J, and then below it, it's a boring phase like a charge density wave. The precise phase that shows up here actually depends on the doping, but for low doping, they're charge density waves. Another claim I won't really be able to get to in detail, but we try and justify it in the paper, is that if you ask what's the critical J once lambda goes to 0, then for low enough doping, the critical J actually goes to 0, and this is the statement that infinitesimal J is sufficient to stabilize superconductivity, even though you have the repulsion. Okay, let's look at the actual phase diagram. So DMRG, you can just trust me that we found the ground state on circumferences, say 8 to 12. I'm going to show data just at a particular circumference. I believe this is 10. And then there's various order parameters we can measure, which I'll get into more detail about to look for superconductivity, to look for anti-ferromagnetic alignment between the two spins, the spins in the two layers. This is AFM XY order. And then we can also check for charge density wave order, and this is what you find. As I said, there's 2 phases, superconductivity at high J, and the coexistence of this charge density wave in the XY order at low J.
What are the dopings you're looking at, like delta?
We do everywhere from 2 plus 1/4 to 2 plus 1. And the phase, the shape of the boundary changes as a function of doping, but it still looks the same. There's still always just these 2 phases. But as I said, actually, the charge density wave, what phases there changes as a function of doping. Like when you're at 2 plus 1, it's actually just a boring integer quantum Hall state. Yeah. All the data I'm going to show is actually from 2 plus 1/4, just to keep things consistent.
So you say it's a charge density wave by measuring the structure factor?
Yeah, we'll see a picture of it. We just measure the structure factor, and you see some stripe pattern develop.
So what is the numerical evidence for what do you measure for superconductivity?
Yeah, so let's do that now. Let's do the hard thing first, which is superconductivity. Then I'll do the charge density wave, and then I'll do the XY order, just to convince you that they're all there. So let's first look at superconductivity. First thing you might ask is, what's the pairing channel? It's basically like S-wave in that it pairs together 2 electrons, which are right on top of each other. But we have 4 components, and what it pairs together, you can see here. It takes a charge in one layer and pairs it with a charge in the other layer with opposite, like singlet-like spin. So up, down, minus down, up. Okay. So in terms of gamma and sigma, the layer and spin, it's this gamma x sigma y is the pairing channel. So in this sense, it's not going to give like P wave or like topological superconductivity. As a phase of matter, it's actually just a BCS superconductor with this pairing. I'm not sure I'd call it S wave though, because they're 2 different layers.
But okay. You guys looked for the other things, like P wave and D wave, but you didn't find it, right? Is that what you're saying?
Yeah, we just revised the paper, and then we explicitly check that there's no P or D wave or anything. You only see this in the S wave channel. Yeah, it's because it's a good question. Now there's a subtlety though, which is superconductivity is of course breaking a global U1 symmetry, but when you're on a cylinder, at long distances, it's like a 1D system, and we know from Merman-Wagner that the order can only be algebraic. So what we check for at any fixed circumferences is you measure the superconducting 2-point function at 2 points distance x along the cylinder. And what we should actually find is that there's a power law with some exponent eta. And indeed, that's what you find. So this is on a log-log plot, the pair correlation versus distance along the cylinder. And what you find is, yeah, it fits a nice power law. There's one subtlety here, which is that when we do IDMRG, there's an accuracy parameter set by the bond dimension. And as you can see, these curves are going from a low accuracy to a high accuracy simulation. All it's doing is converging the power law out to larger and larger distances. And if you want, you can analyze this with the scaling collapse, and everything kind of fits a scaling theory. So it lets you extrapolate to infinite bond dimension and measure an exponent associated with this.
I have a small question about that too, if that's okay.
Yeah, yeah.
Maybe you'll answer that later, but like in the regimes where you find the power law decay of the appearing pair correlation function, is it like the other correlators, the charge and the spin density wave correlators and so on, they have like decay that is like faster than that? Is that true? Or there could be coexistence of things?
That's a good question. So the density, I'll show the fall off in the density shortly, and yeah, it just falls off quickly to some uniform value. Well, the thing is, technically almost any observable, well, okay, it depends on the charge of the observable. Like density in the superconductor, you also expect to have power law correlation. One thing you may or may not expect to have power law correlation is the spin-spin. And I'm not actually going to discuss it in this talk, but it turns out that in the superconducting region, there's a region where the superconductivity coexists with the XY order. And so then you see power law decay in both, and the central charge is 2. And then there's a region where it's only superconductivity, and you only see the power law in the superconductivity. So we check that, but it for the purposes of this talk, I don't really have time to get into the coexistence region. That's a good question. But certainly if you measure the superconductivity on the other side of the phase boundary, it just decays exponentially, for sure. Now, one thing you might wonder here is whether it's just an artifact of the thin cylinder. So how do we know that the superconductivity actually survives if you scale the circumference to infinity? So there's a scaling analysis we can do actually. So you can ask the question, suppose you started out with phase fluctuations in 2D for the superconductivity with a given superfluid stiffness, rho. And then you can just take that XY model and put it on a cylinder and ask, as a 1D model, how does the predicted exponent scale with the circumference of the cylinder you put it on? And what you find is it takes the form I have here. The main point is just that if there is 2D superconductivity, this exponent should scale as 1 over L, right? So it becomes a slower and slower power law the larger the circumference, and that's how it becomes true long-range order in 2D. So you can kind of see this by eye here on the left. We're showing these power law decays of the superconductor at circumference 8 and 11. And by eye, you can fit exponents, and you see the exponents go down the circumference. There's a way to do this more quantitatively in terms of a 2-parameter scaling collapse with circumference and the bond dimension in the matrix product state. And we found we can fit all the data quite nicely with a single ansatz of eta being, whatever, 9.6 over circumference. So it really is consistent with superconductivity over the full range of circumference, scaling to true off-diagonal long range order. I think this is pretty cool. Like, I don't think there's any other, maybe you guys know, I don't know that there's any other 2D repulsive model for all electronic superconductivity where people actually been able to show that it survives in 2D. Like for the Hubbard model, I mean, CCQ's been doing like heroic work figuring out what happens to the Hubbard model on circumference 4 and 6, and like 4 might be superconductive, but then like 6 it isn't. So I was pleased it actually works out nicely here.
So Mike, could I ask you a question about the scaling? So
Yeah.
is this a general statement about 2D and different types of pairing, that the exponent should scale this way?
Yeah, I don't think it would depend on like what the pairing channel is. It's just the physics of the phase fluctuations. Yeah.
So for example, with short range interactions, and let's say in the Hubbard model, if it does have superconducting order, one would expect the same thing you're saying.
Yeah, that's what I would expect if you get one of rel in the Hubbard model. So in the Hubbard model, people have been able to measure this exponent at a particular circumference. So if you could scale it, yeah. I mean, of course, for low L, it deviates from this, but eventually it should reach this form.
Yeah. So your data looks very, very clean. You worried about, so it looks like, so I guess it's open in the long direction. So it looks like the shortest measure you have about 10, distance of 10, and then it goes up to about some tens.
Yeah, so to be clear, it's like infinite in one direction. And what sets how long we like take these measurements is the accuracy of the DMRG set some fall off along the length of the cylinder that you can see saturates at maybe 100 that we've taken, even though physically it's infinite.
I see. So in your calculation, it's actually it's much longer than so you're just measuring and the long distance falls off because of the bound dimension or something. You're actually measuring a much longer cylinder than some tens.
Yeah, exactly. I wasn't clear about that. It's actually, we use translation variant and use an infinite. So we do IDMRG, but nevertheless, you kind of effectively get a length coming from the bond dimension of the MPS, causing exponential decay at some point.
Okay, so that must also be the answer, that you can do 10 or 12 circumference cylinders, while typical quantum chemistry type of things, which also have full matrix elements, I think are limited to much smaller sizes.
Yeah, so it may be that the lattice spacing you should think of is, rather than LB, maybe you should think of the lattice spacing as square root 2 pi LB. And it's kind of ambiguous because it's the continuum. And then this would correspond to like circumference 6 is our biggest or so. So maybe by that sort of conversion, it's not different, but there's not like one way to make that conversion.
Okay.
But I mean, you do need large bond dimensions of 8,000 or something. But compared to quantum chemistry, there's a lot more symmetry here because we have like layer conservation, spin conservation, and then the continuous translation invariance that we can exploit. So it makes it quite a bit more efficient.
Good, thank you.
Yeah. Okay, let's look at the charge density wave. You could actually just see it in a one-point function. If you just measure the density, you'd see a stripe pattern. But I'll show something a little more sophisticated, which is the density correlation function, the pair correlation function in 2D. So the top panel is showing what it is in the charge density wave phase. This is the cylinder, so you know the circumference of the cylinder is running vertically and the length of the cylinder to the left. And you can just see there's this stripe positive correlation coming from the fact that there's a stripe forming. And there's also some like repulsive hole near the origin. So there's like a repulsive hole and then a long distance is a stripe. And we can plot the same thing in the superconductor. You see that far away it's featureless because there's no charge density wave order. And there's actually like this attractive region near the origin, as if the two electrons tend to prefer to be on top of each other, which apparently they do because it's a superconductor.
Shouldn't I have expected for the, or shouldn't one expect for the superconducting case to have some wave-like form, because you should have long-range phase coherence, no? Or I'm mixing
Well,
something.
the thing is, this isn't really sensitive to the phase because this is the density. The phase part.
Oh, so you're plotting here, maybe I'm misunderstanding. You're plotting G of R in the two different phases, right?
Yes, yeah.
Okay, sorry. Yeah, my bad, sorry.
Yeah.
So why do I see stripe and not more like a Wigner crystal form?
It's a good question. It could be that, so this is a subtle issue. So partly, I think it's probably the same 1D physics I was talking about, that there's a continuous rotational symmetry around the cylinder because of the continuum Landau levels. So technically, the Wigner crystal is itself a type of U1 symmetry breaking. So I think probably the picture I have in mind is that it's like, it's basically quantum fluctuating the like relative rotation of the electrons within each stripe relative to each other, that kind of like quantum melts. Technically, we could try and measure, could I guess I could have tried to analyze this by Fourier transforming around the cylinder and see if you can see some small decay, but I don't. But it's actually not entirely obvious that it should be a Wigner crystal. It likely depends on the density. I don't know if you're familiar with like in integer quantum Hall at certain densities. Sometimes electrons prefer to form Wigner crystals, and sometimes they actually form stripes. It depends on the density. So there might be some similar issue here. Yeah, I think we didn't get into it too much because if I go to doping 1/2, turns out it's not a charge density wave. You actually get like a compressible composite Fermi liquid or something. Again, this low phase depends on delta and will depend on various other details if we were to add perturbations to the Hamiltonian. Okay, so hopefully I've like at least quasi convinced you that this model does have superconductivity. Now I want to explain why and use the DMRG to try and test the elements of this hypothesis. So of course we need to explain what the pairing glue is. There's no photons. And the claim is that the fact that we are working with Landau levels, that we have this topology, has an interesting implication for the nature of the charged excitations about nu equals 2, the half-filled Landau level. And the claim is actually that the lowest energy charge excitations are Skermions in that spin texture. I was able to steal a picture from Quantum Magazine from last month. And the cool idea from this paper in collaboration with Harvard is that if your charge carriers are Skermions, the Skermions can get very big. They can like spread out their charge by having a large topological texture. And that causes all the Coulomb repulsion between particles to go down as 1/r, where r is the radius of the Skermion. And then as I'm about to explain, this anti-ferromagnetic term is going to end up causing an attractive interaction between Skermions. Because they're big, that attractive part is always able to win out over the Coulomb part for any J. So that's the claim. Now, some of these ideas are actually related to, say, Tarun Grover and Sentel's study of superconductivity in TIs, doped TIs. Topologically, it's actually quite similar. What's rather different is that we're fully accounting for Coulomb repulsion, which these treatments hadn't done before. They weren't really a study of whether it was energetically realistic. They had just, but they had talked about this possibility of Skermion pairing. Okay, so, but to explain these Skermions and so on, it's going to be useful to give a bit of background on Skermions and the quantum Hall effect. I guess I should be doing a history of Skermions well before the quantum Hall effect and nuclear physics. Tony Skermi proposed the Skermi model. but I'll start a little bit later in the 80s. So let's look at what the plateaus of integer quantum Hall effect look like at some low but kind of moderate temperature. So this is a function of magnetic field. So the low filling factor quantum Hall plateaus are on the right. And you'll see to start the fractions that, or not, sorry, the integers you find is 1, 2, 3, 4, 5. So all of them. And then actually at lower magnetic field, there's a crossover where you stop seeing the odd integers and it just goes 6, 8, 10, 12. Okay. So what's happening here is you're going from a regime in which the spin goes from being polarized, that's where you see all the integers, to a regime where the lambda levels are spin degenerate. Now you might think that the spin degenerate one is the mystery, like, oh, there's a Zeeman effect, of course they should spin polarized. But that's not quite right, because if you look at what the Zeeman splitting is, in gallium arsenide, there's a small negative G factor, and you get a small Zeeman splitting. It's like a half a Kelvin per Tesla. But these integer quantum Hall states, okay, so that is splitting within a lambda level up and down. But the gap you get from that Zeeman term would just be like a Kelvin or something. But these odd integer quantum Hall states are seen at many tens of Kelvin. So if it was just the Zeeman causing this, you couldn't really explain this mismatch in energy scales. And what was worked out by Shivaji Sondhi and others in 1993, and a lot of other beautiful work after that, is that actually the integer quantum Hall effect for an odd integer is an interaction effect. And this is the phenomena of quantum Hall ferromagnetism. So the picture for what's happening, of course, at nu equals 1 is all the electrons just pick, say, the up level to fill into. But the claim is this would happen even if there wasn't a Zeeman term. They would always just pick a direction and polarize the ferromagnet. And the reason is just Coulomb exchange. So you may be familiar with the Stoner model for ferromagnetism. You just imagine you have a spin up Fermi surface and a spin down Fermi surface. And it can be, you can reduce the Coulomb repulsion via the exchange interaction if you polarize it a little bit. Now, the criteria for this happening is that U, the typical strength of the interaction, needs to be greater than the density of states. That's the Stoner criteria at the Fermi surface. But in a lambda level, the band structure is completely flat. So the density of states is infinite. So the Stoner criteria is always satisfied, and you just immediately get full polarization at the lambda level. You can kind of actually work all this out analytically and compute that that leads to a charge gap that's set by the Coulomb scale, E squared over LB, not the Zeeman energy. And that's why these odd integer effects are seen at high temperature, because that's many tens of Kelvin rather than that tiny Zeeman scale. Okay, and there's actually cool experiments, I didn't cite it here, where the G factor of gallium arsenide is pressure dependent, and they can tune the pressure to go to a point where the G factor is 0, so they can actually make the Zeeman energy 0, and they still see the odd integers. That's really like proof it's ferromagnetism.
But does that explain why the polarization disappears?
Yes. Yeah, it will be related. I'll show a picture of that from actual quantum Hall experiments. Oh, actually, sorry. When you said polarization disappears, do you mean as a function of density or?
No, I mean in this plot, yeah.
Yeah, because that Coulomb scale I was talking about scales a square root B. So at low B, the interaction energy is going down, and then there's really two effects. Part of it's that square root B is going down. It's also that when you're in higher lambda levels, the Coulomb repulsion is kind of smeared out because the wave functions become like big.
Yeah. No, that makes sense. Coulomb changes with B. That was the thing that I missed. Yeah.
Yeah, that's the idea. Okay, so the amazing thing about the topology here, and this is this beautiful paper by Sondhi, is that you're probably familiar that if you have like a nonlinear sigma model, because here at each point in space, it's just a vector in what direction are the electrons polarized in the lambda level. We'll call that n. You can form this particular combination n dot dx cross dy. It's a topological term, so it integrates. It's like a total derivative. And what they showed based on earlier work is that the local topological density, which we would call the Skermion density, this thing here, actually induces a physical electrical charge density in proportion to the Chern number of the band. Of course, they weren't really thinking of Chern numbers at the time, so it was just 1. But if you flip the sign of the magnetic field, your Chern number goes from 1 to -1, that would flip the relation here. Okay? So if you integrate this formula, you find that if you put one Skermion into the system, it carries charge 1. Well, okay, it carries a charge equal to the Chern number. So that's its relation. Q physical charge is equal to C times the topological charge, which is the number of Skermions. Now note the Skermions, it's an integer index. So you can have Skermions and anti-Skermions. The anti-Skermion, it just like winds in the opposite way, and that would carry negative charge. So they did calculations and exact diagonalization and so on, and this really is the lowest energy excitation. And this is seen in experiments. It's pretty cool. So they can use NMR to measure the degree of spin polarization in the Landau level as a function of filling factor. These are these experiments from Barrett's just a year or two after Sondi's paper. At filling 1, you have like full spin polarization, and then the polarization very rapidly drops off with filling factor. And you can use this to compute per electron how much spin is reduced. Now, naively, you'd expect from the G factor of the electron that you'd get like 2 Bohr magnetons per electron removed. But instead, you get something like 20 Bohr magnetons. And the reason is because what you're moving is actually Skermions, and those flip the spin in a large region, so they actually deplete the spin significantly. And that's what's being shown here. So super cool. Like this is seen in an experiment that's really charges at odd integers. Charge carries at odd integers. Okay, so how does this physics apply to our model? Well, first let's sit at nu equals 2, because the way we got superconductivity is we started at 2 and then we kind of doped it a little bit. So let's first figure out what happens at nu equals 2. Just like in the integer quantum Hall magnet, the Coulomb repulsion prefers to just like uniformly in space fill 2 of the 4 Landau levels. Okay, and there's many ways to fill 2 of the 4 Landau levels. But this fact that I put on this anti-ferromagnetic term is going to pick a particular way it wants to do it, which is it wants to put density 1 in one layer with a spin, say, pointing along x, and then density 1 in the opposite layer with the spin polarized pointing along -x. I mean, anyway, I just want the spin to point equal and opposite. Now, of course, it doesn't care where in the xy plane, because you have this, you still have this, it's an x at z, right? So it doesn't care x versus y. This is where the lambda term is important. For positive lambda, it wants to be in the xy plane. If you do set lambda equals to 0, then it doesn't care whether it's in the xy plane or along the North Pole, okay? So this is what we call the xy anti-ferromagnet. But note when I say anti-ferromagnet, it's only because the top layer is opposite to the bottom layer. But as a function of 2D space, it's completely uniform in the ground state. They're all pointing in the same direction. Is that clear? So do we actually see this in the DMRG? We do. The order parameter you would measure is this like layer resolved spin density, the difference between the spin and the top and the bottom. That gives the anti-ferromagnet. And for the same reason as the algebraic superconductivity, on the cylinder, you expect this to be algebraic, and you see power law decay with very small exponents, indicating it's a really strong order with the same 1/L scaling I talked about earlier. Okay, so you start out with this XY anti-ferromagnet, and you can measure the charge gap. It's a very strong insulator, so the gap to add an electron or a hole is about twice the Coulomb scale. Okay, so that's our parent insulator. And now you can ask, if I add 1 electron or 2 electrons to this parent insulator, might they go in as Skermions for the same reason as in the integer quantum Hall effect? It's interesting now, because if we only add a single Skermion to, say, the top layer, you'll end up with a spin texture which looks something like this. In the bottom layer, it just keeps pointing, whatever that direction was. And in the top layer, far away, it's happy. They're going to be anti-aligned. But in the region of the Skermion, by definition, the spins are no longer anti-ferromagnetically aligned. So near the core of the Skermion, you lose this like J term. You have a penalty from that. And that actually makes a single Skermion in one layer fairly expensive because it costs energy at the core. Okay. So is there a different way to put charge into this system that might do better than this Skermion, single Skermion in one layer? And the answer is yes. Actually put two Skermions in, or to be more precise, put a Skermion in the top layer and always have the bottom layer do exactly the opposite thing. So have the spin density n minus be negative n plus. Now, the interesting thing is I said that Skermions have antiparticles, and indeed, if you take n and just flip the orientation, that makes it anti-Skermion, okay? So if you make a Skermion anti-Skermion and have them sit on top of each other, the anti-ferromagnetism is always happy everywhere. You get a configuration that looks something like this. Okay, so, but what is the charge of this object? So using this formula, on the top layer, it's churn 1 and a positive Skermion, so that's charge 1. The bottom layer, I flip the sign of the magnetic field, so it's churn -1, and it's an anti-Skermion, and -1 times -1 is 1. So actually, both of them are still chargey objects, and altogether, this thing, if it binds together, is a charge 2e object. When you work out statistics, it's just a conventional boson, just like 2 electrons would be. Okay, so this paired Skermion gives you a charge 2e boson in the system, which naturally could lead to superconductivity. So that's cool, but is this actually energetically what happens? So yeah, it makes J happy to put the Skermion, anti-Skermion on top of each other. But clearly the whole thing that's interesting about our study, I think, is that there's one over our Coulomb repulsion. The Skermions, because of that, don't want to sit on top of each other. This is what makes superconductivity in general difficult. So is this charge 2 object actually favorable to bind? So quantitatively, the thing you want to do is start at nu equals 2, and then in DMRG or ED or whatever, you first measure the energy to add 1 electron, call that E1e, and then you measure the charge to add 2 electrons, charge 2. And then you measure this pair binding difference, which is 2e1 minus e2. And if you get something positive, it means it's that basically gives the binding energy, which forms the Cooper pair, the pair. So we'd like to see if this is actually positive. So we're going to compute it 2 ways. Once, appealing to this integer quantum Hall ferromagnetism business, we can do a kind of classical calculation using a nonlinear sigma model. But then finally, we're going to do the full quantum thing and just solve for the excited states in DMRG and calculate their energies. So this is a kind of picture. Well, okay, let me just get to the nonlinear sigma model. Oh, I'm going to go, okay, I better accelerate this actually.
Yeah, I mean, you can go past 12:30. It's, we kind of reserve the slot till 1, including questions, but it's up.
Okay. Okay, well, I'll push forward a bit more then. So how does this nonlinear sigma model work? It's kind of taking the same nonlinear sigma model treatment that's developed in Sonji's paper, and you basically take 2 copies of it, one for the top layer and one for the bottom layer. So the way it works is you have the spin direction n. This is a vector labeled by the layer, so there's 2 of them. And one term in the Hamiltonian is just the elastic energy. It doesn't, I don't know, there's some stiffness to the ferromagnet. And this G can be computed analytically in terms of the Coulomb interaction. Okay, so we know the stiffness. Now, another term in the Hamiltonian is I told you that when you have a Skermion, so this particular weird combination of derivatives, that induces physical charge, and those physical charges interact with the long-range Coulomb repulsion. So we need to keep that term in the nonlinear sigma model. And then there's this anti-ferromagnetic pairing between the vectors in each. Okay, so you have a competition between these last 2 terms to determine if there's pairing or not. So what we did is we can actually just numerically solve for the lowest energy ground state as a classical thing. You can just discretize it and solve the PDE or whatever to find the ground state. So it should be, and I did that. But let me give you the intuition for how it works out. So if you make a Skermion of a typical size R, so R is kind of like the volume over which the spins are different than everywhere else. It's able to reduce this middle Coulomb term part because just rho becomes, the density becomes distributed over a bigger region. And the key thing here is that in 2D, this elastic term is actually scale invariant. So if you just take a Skermion and just scale it up, double the size, it doesn't cause any different elastic energy. So as far as Coulomb is concerned, within one layer at least, it just wants to make really big Skermions. That explains the findings in the quantum Hall context. Now, what if you have two Skermions, one in the top and one in the bottom? Well, if they both have size R, when they sit right on top of each other, the Coulomb interaction kind of gets smeared out over that size. So the biggest Coulomb repulsion they can see is actually 1 over R, even if they're right on top of each other. On the other hand, as I told you, like the Skermions, if they're not on top of each other, the J term is getting violated. Whereas if they're on top of each other, the J is always happy. So that leads to a kind of attractive part, which goes as J times the size of the Skermions. And you can see from this that as long as you make the Skermions big enough, the J attraction always wins out over the Coulomb repulsion, and we expect pair binding. So that's the basic physics here for why small j can lead to pairing.
So is that true that if I replace the Coulomb interaction with the V1 suitable potential or shortening interaction, it cannot stabilize superconductivity?
No, I think that would be fine because the thing is that when you put this short range like delta function interaction, but then project it into a lambda level, what it really becomes is like a Gaussian. Well, I need to think about your problem. It's a great question. You need to think about it a little more carefully. I think the answer is still that it's actually even better than this, because what happens is that like I think the interaction will end up going as 1 over R squared in that case rather than as 1 over R. So it'll be even better.
Hi.
I should say here the Coulomb repulsion does the thing we would expect. It's bad for pairing in any situation I can think of. So if you make it shorter range, generally you have better pairing.
I see. That's interesting.
Hi, I have a very now question. Like,
Yeah.
so here we see there are 2 layers. Are these 2 layers like the real layers, or it represents like the valleys or some like?
Yeah. So I've called it layer just because I like drawing it that way, but in actual magic angle graphene, it will be related more to valley. I'll get to that at the end.
Yeah,
Yeah, and because I should emphasize that the Coulomb repulsion is not weaker between the 2 layers than it is between the 2 layers. I use a completely like symmetric Coulomb repulsion. So in that sense, that's not physically like layers because they're not separated in space.
But so the radius here is like it's still the real radius, or it's?
Yeah, it would be like you see these like E blobs. It would be that radius. Yeah, because they are just sitting right on top of each other. So when you go to compute the Coulomb repulsion, there's no like distance term in the like spearing out the 1 over R. Yeah.
Thank you.
Yep. I think the pairing would become better if you made it layers, just for the obvious reason that if they're farther apart, it's easier for the 2 of them to sit on top of each other because there's less Coulomb repulsion. We didn't check that case, but.
So if I make the 2 layers separated by a distance, by increasing the distance, how will that affect the pairing?
Well, so it depends if you keep J the same. So if you allow yourself to keep J the same, but just makes them farther apart, it will almost certainly make the pairing easier, just for the intuitive reason there's less Coulomb repulsion between them, where the J is staying the same. The reason it's hard to imagine how you would realize that in experiment is, as I said, generally the actual physical origin of J is coming from some tunneling, some hopping between these two things. So as you separate them, you would reduce J, and naively that part would actually decay much faster than the Coulomb part, and then you'd, yeah, it would be bad.
Mhm.
Yeah.
So the picture will be simpler if I keep J constant, but set D equals infinity.
Yeah, but then it's like kind of trivial because you've just like, you've removed, like, superconductivity isn't really surprising if you don't have Coulomb repulsion, you know? I mean, that's, well, the thing is, like, when we do mean field treatments of superconductivity and you're not actually doing like Eli-Ashberg theory and solving for phonons, yeah, you just ignore Coulomb repulsion, you put in the attraction, and then indeed you find superconductivity. I mean, the kind of magic though is that you do have Coulomb repulsion, and generally with phonons, the reason it works is because of like retardation and screening and all this stuff.
Mhm.
I mean, that's not what's happening here, but indeed, if you just set D to infinity, there's no Coulomb repulsion between them, and they'll bind because of J.
Mhm.
So it's really like this energetic aspect, which is surprising to me, that even if they're right on top of each other, you get pairing. So the first thing I'll show you is just, we solve for the ground state of the nonlinear sigma model, and then we measure, you can either do it with 2 charges in the system or 1 charge. And then we measure this pair binding energy. And as a function of J and lambda, it looks like this. So everywhere red, they want to form charge 2 pairs. In the blue region, they would instead fly apart to 2 charge 1. So there's no pairing. Now at lambda equals 0, it kind of does what I said, where you can see to arbitrarily small j, you get pairing. It goes down with j, but it's always positive. But with lambda, lambda is clearly bad for the pairing, as you can see. So what's happening here is, I've been talking about Skermions, but Skermions strictly only occur in the SU2 symmetric point where lambda is 0. If you take the nonlinear sigma model and put on this easy plane, so lambda prefers everything always to be in the xy plane, then what's known is that Skermions actually slightly separate into 2 objects called merons. They're basically like vortices in the xy parameter. We can see that in our nonlinear sigma models. If you look, so this right panel here, the purple and green, this is the charge distribution in the ground state. And you see that rather than making one blob, it's slightly, the charge splits actually. It's not splitting far, they're just like a couple magnetic lengths apart. And that's the fact that with lambda, the Skermion splits into a bound meron pair. But what's happening is that everywhere in the red region, the merons stay bound together, whereas over here, they then fly apart. And you can understand this curve analytically, that merons have more elastic energy, and that's why the required minimal J goes up. Shubayu has some nice analytic calculations which make this purple line prediction here, which seem to fit pretty well. Okay, so that's a purely classical treatment, but now we want to just solve the full quantum Hamiltonian for that Hamiltonian I said. And in DMRG, we start out by getting ground state at nu equals 2. Then we can do finite excited state DMRG to just calculate the lowest energy state with either charge 1 or charge 2 in it. And then you find the difference of those 2 energies, and that tells you the pair binding energy. You can see the result on the right. I apologize, it's in a slightly different like range of J and lambda. But you can see for small lambda, big J, there is indeed a positive pair binding at the fully quantum level in DMRG. And the magnitude of it is actually very similar to the nonlinear sigma model. It's about the scale J. So that's cool. So there seems to be, this doesn't necessarily prove there's Skermions yet, but in DMRG, there is a pair binding energy to make pairs, despite the Coulomb repulsion. You'll notice there's some quantitative differences in where the phase boundary is. We can actually understand this. Shibuya did a very cool calculation where he went beyond the classical nonlinear sigma model by going to first order in H bar, including the quantum fluctuations to the saddle point solution. And those induce some 0 point energy that increases the energy of the Skermions. And he can show that that leads the actual phase boundary to kind of bend upwards, just like we see it does in DMRG. Okay, cool. So charges coming in as pairs.
So Mike, sorry, another technical question. In the DMRG, why do you do excited state as opposed to add and remove to get this pairing energy?
Oh, it's the same thing. I mean, the charge 1 eigenstate is the lowest energy state with charge 1. So it's the ground state with charge 1, I guess.
Mm-hmm.
But I mean, I would kind of think of that though as like an excitation on top of the charge 2 state. Yeah.
Good. So it is sort of a ground state, but different sector ground state. So then, do you run into trouble with large finite size effects? This is really technicality now, but because of the Coulomb interaction, do you want to get this energy difference, which is not a large quantity?
Yeah.
Do you know that mirror images and so on with long range, if you in the
absolutely.
cylinder direction, do you get in trouble with that? Or?
Yeah, so if you measure any one of these, like E2E or something, we do it as a function of circumference, say 12, and you absolutely see like 1 over R or 1 over L changes because of the Coulomb repulsion. So when we do this subtraction, you still see changes as a function of circumference. The data I'm showing here, it's extrapolated as a function of circumference using 8 to 12. So Shibuya has a kind of, it's kind of momentous calculation I'm hiding. I mean, he calculates a range of bond dimensions from like 2,000 to 10,000. And then the circumferences, and then he does a double extraction. But even if you just took a single circumference like 12, I'll show some unextrapolated in a little bit. What you would find is that the minimal J required for finite circumference is finite. Like rather than being 0 here, it starts at like 0.2 or something. And you can actually work out that's expected when you put the Coulomb on the cylinder, it pushes up the critical J. So the fact that J goes all the way down to 0 only is true once you extrapolate to 2D. So I didn't put in this talk, but we think through those issues, and it's in the appendix.
Okay, thanks.
Yeah. Okay, so pairing would actually not be enough for superconductivity. So for instance, you could get these charges might enter as charge 2 bosons, but then maybe they could, I don't know, form a Wigner crystal or something, right? To get superconductivity or a Bose-Einstein condensate of these bosons, they need to have dispersion, which is what establishes phase coherence. Okay, so we need these charge 2 things to move around. Now, at first, it's a little bit puzzling because we started with completely flat lambda levels. There's no dispersion at the single particle level. So how is it that these charge 2 things can actually move around? And there's a really cool effect here, which it turns out that the topology is able to convert the interaction energy into a dispersion energy. And here's how it works. So suppose you have these 2 Skermions, and suppose you boost them both to velocity v along some direction. Now, because they experience equal and opposite magnetic field, they're going to start feeling a Lorentz force, which pulls them apart. Okay, so that's F is equal to EBV, of course. And now what's going to compensate that Lorentz force is, as I said, the anti-ferromagnetism and so on mediate some effective binding interaction between them, U binding. And so that will establish for a given velocity a preferred distance between them where the Lorentz force balances this kind of elastic energy, the spring, which is tying them together. Okay, and that spring, the binding energy, is coming from the interactions. So if you just work through this and Taylor expand to lowest order of the binding energy. You assume the binding energy is, kr squared, just like a Hooke's law, and then work out what the energy is as a function of velocity. You find a quadratic dispersion relation with a mass set by whatever the Taylor expansion coefficient, the Hooke's law was, which in this case, at least at the classical level of the nonlinear sigma model, ends up being J in the appropriate units. Okay. So this topology, the effective Lorentz force, converts interaction into a dispersion relation for the pair. This kind of thing actually shows up in fractional quantum Hall physics in explanations of composite fermions. So for some of you, this sort of argument might be familiar. There's this general rule for composite fermions. It's known that composite fermions are dipoles that carry momentum perpendicular to the dipole moment. This is a like twist on this if you particle hole conjugate partly. That was probably confusing, but we can talk about it after. Okay, so do you see this in DMRG? Here, there's a lot on this curve, but let's focus just on two things. The solid circles are what you get by finding this charge 2 energy, the excitation of the charge 2 thing, as a function of momentum around the cylinder. So our numerics conserve that momentum, so we can find the lowest energy state for a given like targeted momentum using the conservation law, and use that to kind of get a dispersion relation, but our resolution is super coarse. The different colors are what system size you can do it on. So let's just look at, say, the lowest and the biggest. Okay, so the blue one is the lowest, starts out at 0 energy, goes up, and then you can see it kind of saturates at around 0.2 in these units. The energy of the pair like saturates and falls down a bit. And then what's happening as you increase circumferences, there are, like you asked about, these big finite size effects. The energies drift, but it's doing something nice. At the biggest, again, the energy goes up and then it saturates. And if we took the next data point, it would basically be flat beyond this point. Okay, so it's because of the finite size effects, I'm not going to claim we've measured the dispersion relation, but the point is the energy versus momentum curve is non-trivial. It goes up and then at some point it saturates. Now, the classical estimate from the nonlinear sigma model is this dash parabola here, and it agrees to within 20% or something up until the saturation. Okay, so I can actually give you a picture for why this saturation is happening. I told you that as you increase the velocity, the Lorentz force is ripping the Skermions apart. So what happens is once K is big enough, the Skermions get pulled far enough that they lose this binding energy and then they just kind of fly apart. So then the energy no longer depends on momentum anymore because they're already like far apart. We can see this actually. So what I'm showing these simulation in these pictures here is, let's focus on the left one. This x-axis is the distance along the cylinder, and then I measure just the charge density in this eigenstate with charge 2 in it. And then I guess I'll call it the y-axis here is the momentum. And so what we can do is just look at how is this charge distribution of the Skermion pair evolving as a function of momentum. And you see at the bottom of the curve, like inside the parabola part, the charge forms one big blob with charge 2e because they're bound together. And then as advertised, as you go to larger momentum, the charge distribution separates actually into two peaks with charge 1e each. That's the pair getting ripped apart by the Lorentz force. So pretty cool. And on the right, we show it in the layer resolved way where we can separately measure the charge density in one and the other layer. And you can indeed see that the charge distribution slowly separate and then just fly apart. So that explains the saturation here. Once they're far apart, the energy doesn't depend on momentum that much. Okay, so this is the best we can do as far as like giving you a picture of the Skermion. It's that thing, that blob right there. Like at the quantum level, there's no picture like this because it's quantum disordered. The spins are actually fluctuating and so on. So we can't like measure the spin and see them because it's quantum disordered. Okay, so we've shown that there's pairing, we've shown that there's dispersion, and when you put those two things together, we would expect Bose-Einstein condensation that explains the superconductivity. And you can actually check this kind of quantitatively in the sense that if we measure where that boundary was for the pair binding energy in the DMRG and plot it on top of our superconducting phase boundary, the pair binding energy is this white curve here. And you can see quantitatively, like, except for right at lambda equals 0, which I don't quite want to get into. It's a finite size effect, we understand, but up here it starts agreeing. There's other aspects we investigate. This isn't the only evidence, but I'll leave that to the archive post. Okay, so that's, let's see, what time is it? Oh, it's 12:40. Oh, well. Let me just say so quickly, magic angle, our motivation for this is explaining magic angle twisted bilayer graphene, or at least is the original motivation, and more recently twisted trilayer. Where this comes about is the following. So you have in magic angle graphene, you have 8 bands, flat bands. Just ignore the spin for now because spin won't play a role. The 4 orbitals I've been talking about are actually the valley and the fact that you have 2 bands at any momentum point. So where do the lambda levels come in? There's this beautiful lambda level picture of magic angle twisted bilayer graphene going back to the work of Jose et al. In 2012, more recently Ashwin's group. What they show, the magic angle graphene has this cool limit where if you artificially turn off the interlayer hopping between the A in the top layer and the A in the bottom layer, the model at the single particle level becomes exactly solvable. And you find that the eigenstates have 2 properties. One, sublattice A versus B becomes a good quantum number. So your band structure can be labeled by sublattice in addition to valley. And 2, the bands, rather than just being pretty flat, are exactly flat. And they carry churn number either plus or minus 1. So the way it works is the 4 bands, because we're looking at one spin, you can label by valley and sublattice, and Ka and K prime B have churn 1, and Kb, K prime A have churn -1. So this is exactly where we get what I've been calling the quantum Hall bilayer. It's really churn bands in magic angle graphene that come in time reverse pairs. Okay, so my layer is churn sector, and what I've been calling spin is actually within one churn sector, there's a valley K contribution and a K prime contribution. So my spin is actually valley in magic angle graphene. Okay, so that's the translation. Yeah, there's evidence for this lambda level picture. I'll leave it at that. Now, where does the anti-ferromagnetic coupling come from? Well, that picture was in the chiral limit where the bands were perfectly flat. Really, there's a little bit of dispersion. And Eslam did this beautiful calculation. If you look at the form that this dispersion takes in the lambda level picture, it looks like a tunnel coupling, a hopping between the churn 1 and the churn -1. And you can do a perturbative second order perturbation theory in the hopping, and you find that it exactly leads to this super exchange anti-ferromagnetism between the 2 churn sectors. So that's the origin of the J. And when you do this calculation carefully, because valley really only has a U1 symmetry, not like a full SU2 symmetry, you also get a lambda term at the same time. Okay, and then finally, we needed to have this XY state at nu equals 2. In the magic angle twisted bilayer graphene language, this is what we call the intervalley coherence state. So when we do both Hartree-Fock and DMRG on the actual Hamiltonian of magic angle twisted bilayer graphene, to the best we know it, and try and ask what's happening at this nu equals plus or minus 2 moninsulator, we find it's this intervalley coherence state. And there's more recent work from Princeton as well, which is also in agreement with this. So as I said, because valley is pseudospin, intervalley coherence means you're spontaneously going into a superposition of up and down, like valley K and K prime. That's exactly like order in the XY plane. So under this mapping, this intervalley coherence state is the XY order I talked about. Now the energetics here are kind of delicate, like this X and Y order is preferred over the other ones at the order of like half an MeV or less. It's really small. So, I wouldn't be shocked if in the end there's just some term in the Hamiltonian we don't know well and it's not this KIVC. But with our current best understanding, it does look like the KIVC if it's when you don't have strain. Okay, and you can kind of try and convert from magic angle graphene to the parameters R model, and you get something like lambda equals 0.1 and J is between 0.05 and 0.3, though you shouldn't take it that seriously. They're like different models, so we have some heuristic for converting. But anyway, but the point is that it's not like a crazy part of our phase diagram. It's close to where we could get pairing. Okay, so the ingredients are there in the magic angle graphene. That was a somewhat maybe not an even-handed discussion. I'd give it maybe a 40% chance of working rather than as sure as I might have sounded. We know from this lambda level DMRG numerics that in principle, this idea of Skermion pairing is microscopically viable. The energetics work out. But how can we tell in the experiment if this is actually what's happening? We don't really know yet. It's a good question we're thinking about. And it's difficult because the superconductor you get from pairing Skermions, even though it sounds exotic, in the end, it's just like a BCS order parameter and it's not topological. There's no Majoranas, there's no edge states. So the superconductor itself isn't that interesting. It's just the energetics of how it got there. And also this putative insulating state, the IVC or this XY order, if you ask what is it physically, this is kind of a blast from the past of the cuprates, it's alternating loop currents, which are really difficult to see because like at the level of graphene, there's clockwise and counterclockwise currents. When you zoom out, you don't really see anything. You need some way to like image currents at this like nanoscale, which we don't know how to do at the moment. I don't know, maybe there's some way to use the Kerr effect or something to. Okay, but I mean, so in this sense, the experimentalists are sort of ahead of us. They've been doing a lot of amazing experiments with STM, thermodynamics, nanosquids, etc. I know, so we're still looking to find what tests exactly we should do to see if this is what's happening. Okay, and with that, thank all of you. I really enjoyed the questions. It makes it much more nice to actually hear from you guys. Sorry, it's a bit late. Thanks.
Thanks. May I ask 2 questions?
Yeah.
The first is, have you, about numerics, have you tried doing, for the lambda level problems and the superconductivity, have you tried ED for that? And whether ED is limited by system size?
Yeah, I mean, you would probably know better than I do. I mean, clearly it's difficult because you have 4 components in a single orbital. So the size of your Hilbert space goes as 4 times the number of flux, choose 2 times the number of flux. So I don't know how many orbitals you could solve, like 5 maybe or 6, I'm not sure.
So it's, but the filling fraction is half filling.
Yeah, it's half filling. You have more symmetry. So if you make use of all the quantum numbers, you could probably do better than just doing like, yeah, I mean, it's easier per orbital, but you still won't be able to do that many flux.
Okay.
And the other thing, there'll be the subtlety. Maybe you'll be able to see Skermions. I'm not sure. It'll be subtle that just like the XY order is only algebraic in 1D, seeing the symmetry breaking would require like scaling analysis and so on. Because, but I mean, we could talk. Maybe you'll be able to see the Skermions. I'm not sure. Using like Ed Rezai was able to see Skermions back in 1993 in exact diagonalization. So. Maybe that's what 20 years has bought us of.
Yeah, my second question is about the analytics. I think since the lambda level wave function is very simple, it's holomorphic wave functions, is that possible to construct the superconductivity wave functions, even at least at some limit, for example, trivial limit, the d equals infinity, as you said.
Yeah, that's a good question. Yeah, it might be. It might be actually. It's a good question. So there's a nice picture for like an analytic onslots for Skermions in the integer quantum Hall effect using the holomorphic gauge. So one could try and adapt that and have 2 copies, but the thing I think is subtle is that if you have a single Skermion in the quantum Hall effect, it doesn't move. So it's happy to just sit somewhere because it's in a magnetic field, its momentum is quenched. Whereas in this case, as soon as you put two of them together, it's able to start moving for that reason I said. The net thing doesn't expect to acquire a Berry curvature. So the object doesn't want to sit still. It lowers its energy by going into a superposition. So at least at the moment, I don't quite know what the ansatz would be, but there probably is an ansatz, kind of like with a CFL, where you can think of it in terms of dipoles. There might be something similar here. Yeah, if you have any ideas, that'd be fun to talk about.
So far I don't have any idea, but maybe we can talk afterwards.
Like, I was also wondering when you said that you did the calculation for actual TBLG, like, what does that mean? That still entails a model of some kind, right?
Yeah, so that's actual. Let me edit that right now.
Well, you may have put quotes on it anyway. Yeah, so
no, it was italic, which makes it sound like it's very serious. Well, we take the Bit-Switzer-McDonald Hamiltonian using parameters from DFT to the best we can. And then for the Hartree-Fock, say, we just project the Coulomb interaction into the lowest, say, 20 bands about the Fermi surface, and then you do self-consistent Hartree-Fock. So we don't need to form Bannier orbitals or anything like that. You just work in K-space and just solve that model. It's the same sort of model that, say, Biao and Andre have been studying, et cetera. For the DMRG, we do exactly the same thing. It's just that we only have the computational firepower to do the two, the flat bands, the two bands closest to the Fermi level. And you put it on a cylinder and solve for the DMRG ground state.
So maybe I could jump in there, Mike. Do you, so from that, what is your sense of what's most needed to go beyond? Is it the limitation of, only a small number of bands? Is it a limitation of the model? What is your sense?
Well, my sense is, so the Hartree-Fock arguably might work well at the integers, but it will completely fail. So one interesting thing we find is that the Hartree, it depends on the filling you're at, but like at nu equals 0, the Hartree-Fock Slater determined ground state ends up being extremely close to the DMRG ground state in general. So like at integers, Hartree-Fock seems pretty good. But we expect, precisely for the possibility of the fact that you have these like soft modes, these fluctuations in the order parameter, that as soon as you dope away from the integer, Hartree-Fock will be completely wrong and we need to do DMRG. Okay, and the problem is that nu equals -2, we can do the DMRG on circumference 6 and like converge it okay. We of course want to just dope it and see if we get a superconductor, but the entanglement is just really hard in DMRG. Maybe we'll eventually be able to do it and it'll just like take a month to run or something. But so at the moment, our limitation is just how long it takes to run when we dope it from a numerical point of view. Now,
but you think that model, if you could converge, if you could get the DMRG to converge, you think that model is a good?
Well, I mean, it's what. Well, I'll say it's the model that thousands of hours of high-paid academic lab power have been working on, whether it's Bernavig's group or Ashfin or McDonald. They're all basically studying this model. And some things about the experiment it seems to give right, like gives reasonable value for the band gaps at -4 and 4. You end up getting, if you compare with STM, they see these two peaks in STM and it kind of gets the splitting right there. So, at the level of 20 MeV, it's probably basically right. The issue is, like, do we really trust all those terms in the Hamiltonian down to the MeV level? I don't know. Probably not. So what one needs to do ideally in all of these numerics is make a phase diagram as a function of theta, dielectric constant, the details of the interlayer hopping, and see how robust any of this is. And for the insulator, we've done that, and we kind of know like, oh, at a critical strain value, there's a phase transition or whatever. Superconductivity, I don't even know if we're going to find it. Anyway, so I hope we find it, but I don't know. Everyone's assuming that you can get it from this model. Not everyone. There's kind of two camps. Some people think we're going to need to add phonons, and some people think this model is enough. That's kind of the big question. So hopefully maybe DMRG can actually answer that.